Hi everyone. Today we're going to be talking about the Rham's theorem. Rham? Duran? I don't know. So Rham's theorem tells us that two cohomology theories, singular cohomology and de Rham cohomology, agree on smooth manifolds. So let's quickly review de Rham cohomology. De Rham cohomology starts with your differential forms. So we have this chain complex where we start with the smooth functions. Then we can take the differential and we get one forms. Well, it takes us into one forms. Can do the differential again. The exterior derivative we call over here. That'll take us to two forms, etc. And then we go up to the dimension of the manifold, which we'll say is m. If you do any higher exterior derivative, you'll get 0. So this gives us a cochain complex. We use some different words than we do in singular cohomology. Instead of saying cocycle, i.e. something which has exterior derivative 0, we'll call this a closed form. And then instead of saying coboundary, say exact. So differential forms in another language are also the things that you can integrate over. So in order to show that the de Rham cohomology agrees with singular cohomology, we're going to follow a very similar sort of pattern to how we proved that Poincare duality works, where we have these two sort of cohomology theories on a manifold and we show that they agree. So what is the strategy? Well, let's talk about strategy. First, we define a homomorphism. I guess this is for every manifold. We'll define a homomorphism from the de Rham cohomology, which we denote HDR of K, but maybe I'll use P, M, to H P of M. It's a singular cohomology. And then 2, we will, the overall strategy is going to be a sort of induction on Merivia-Torres. So maybe I'll say, or step 2 is induction on Merivia-Torres. And the way that we have to do induction is you first prove a base case, and then you do the induction step. So we're similarly going to have, maybe I'll call it 2.1, base case. So I'm going to call this homomorphism I. Show I is an isomorphism or the special type of manifold we'll do is a contractible manifold. And then 2.2, the induction step. And to do this induction step, there's going to be a few pieces that we'll need. So we're going to need stuff like I is natural, and it commutes with the connecting homomorphism. In Merivia-Torres. The Rham versus singular cohomology. So let's start by defining the homomorphism. So an element of the de Rham cohomology is an equivalence class of a differential form. And a differential form is exactly the sort of object that you can integrate over p-dimensional submanifolds of your manifold M. On the other hand, an equivalent or an element of the singular cohomology is an equivalence class of a cocycle, which is in particular a cochain, which is something that gives a number to simplices in your space of dimension p. So I should have said this earlier, but whenever we're doing singular cohomology, we're doing it with R coefficients, since really the Rham cohomology is all over R. It's manifolds. So we're given an object which can assign real numbers to submanifolds, and we want an object which can assign real numbers to simplices. It's going to be a problem because some simplices are really screwed up. They're totally not smooth. They might be continuous, but I don't know, they're horrible. So we want to map this to, what we would want to do is say, okay, well, this should be an equivalence class of something which evaluates simplices. So let's say if we're given a simplex or maybe even a chain omega or sigma, this should map to the integral over sigma of omega. This is supposed to be an assignment of simplices to real numbers. That's what cohomology should do. But in order for this to be well defined or to make any sense, we kind of have to define this notion of integration or simplify it. So one thing that we can do to make our lives easier is this singular cohomology by the universal coefficient theorem is just the dual of singular homology. So I should write like this. It's hom from singular homology, oops, and M to the real numbers. Now, a technical theorem that I'm not going to go into is that we can replace this singular homology, where really we're dealing with any sort of continuous chains, continuous simplices. We can replace it with the theory of smooth simplices. The idea behind that proof is normally you get homology by considering the chain complex, which will denote C hash of M. This is the chain complex of simplices. We're going to replace it with a different chain complex, which I'll call C hash infinity M, which is the chain complex of smooth simplices. Where smooth simplex is, if we consider a simplex as a manifold with corners, we want the map from this manifold with corners to M to be a smooth map. Then what we can prove is that these two chain complexes, well, every smooth simplex is in particular a simplex. Simplices. So we have this inclusion pretty naturally, and we're actually going to, the thing you would do is use the Whitney the Whitney approximation theorem or some version of Weierstrass's theorem to approximate your continuous simplices in a sort of natural way to create a map going backwards. And we need to prove that these two maps form a chain homotopy equivalence. And this chain homotopy equivalence will say that the homology you get from your normal chain complex of simplices, the continuous version, is the same homology as you get from the chain complex of C infinity simplices. So we can say, replacing this, we can say that HP, the singular cohomology, is isomorphic to hom from HP infinity, the smooth homology theory, the smooth singular homology. It's a little funny that we use the word smooth singular. It's like I don't know, whatever. So now that we're in this world, we actually can define what it means to integrate over a simplex. So now we can say when omega is a C infinity simplex, sorry, when sigma is a C infinity simplex, we define the integral over sigma of omega. We define this to be the integral over the manifold with corners delta n, I guess delta p. Let's say this is a p simplex, and omega is a p form. We say that this is the sigma pullback of omega. And then we can similarly define, if we replace sigma with a sum of simplices, so we say that sigma is instead a chain, well, we just use linearity to extend the definition. So in this way, we actually can make this definition here, where we take a differential form, or an element of the Rham cohomology and equivalence class of a differential form, and we can map it to the cohomology class, which is assigning a smooth chain to the integral over that smooth chain by omega. Now, there's a few things to check. We want to check that this is well defined on the equivalence relation. I guess we should also check that this map is a cocycle, that it sends cycles to 0. And that's not hard to see. So if omega is a cycle, sorry, let me use a different color. This is the well-defined image, let's say. Need to check that it's a cocycle. So let's try it. Let sigma be a cycle. Then the boundary of sigma equals 0. So we get that the integral of sigma omega, cocycle. Cocycle is not one that sends cycles to 0. It's one that sends boundaries to 0. So let me do that correctly. Oops, I broke the whiteboard. Let me restart that. You're not seeing any of this. All right, so where were we? So to check that something's a cocycle, we need to say that sends a boundary to 0. So let boundary of sigma be a boundary. Then the integral over the boundary of sigma of omega by Stokes' theorem, we'll get a similar Stokes' theorem for this integration on chains. You prove it using Stokes' theorem for manifolds and corners, will be the integral over sigma of d omega. And since omega represents an element of the cohomology, the Rham cohomology, that means we're assuming omega in the first place is a closed form. So this is the integral over sigma of 0, which is just 0. So indeed, we get a cocycle. Then the other thing to check is that well-defined up to exact forms, i.e., we would want to see that if we used, if instead of picking the representative omega, if we picked the representative omega plus d eta, these both represent the same cohomology class, since this right here is a coboundary, it's an exact form. We want to see that we get the same answer on the right-hand side. So really what we really need to show is that exact forms are sent to coboundaries. And a coboundary is a coboundary is a cochain which sends cycles to zero. So how should we do this? Let's say let d eta be exact and sigma a cycle. Then we want to show that this integral is zero. Let's try doing the integral of sigma d eta. Well, by Stokes' theorem, this is the integral of the boundary of sigma of eta. But since sigma is a cycle, the boundary is just the empty set. So this whole thing turns out to be zero, which is exactly what we wanted. So this definition is well defined, and we actually do have a homomorphism from the de Rham cohomology to the singular cohomology. Now the next and longer task is to show that this whole thing is well defined, or that this whole thing is an isomorphism. So that brings us on to step 2. So we're going to start with 2.1, which is the longer of the two. 2.1, the base case. So our base case is going to be contractible manifolds. So contractible, in other words, manifolds that have the homotopy type of a point. These are the manifolds that, in terms of their singular cohomology, we're going to have H0 of M. Let's say it's connected, for example. Let's say contractible is connected. So H0 of M is going to be isomorphic to, remember we're doing this all with R coefficients. I might drop the R, but it's always R coefficients. This is going to be isomorphic to R, whereas all of the higher cohomologies are going to be 0 for P greater than 0. This is the singular cohomology case. And what we're going to need in order for I to be an isomorphism is that the de Rham cohomology at 0 and P for contractible manifolds exactly agrees. We need to show a little bit more that on the degree 0, I actually is an isomorphism of R to R. It's not like the zero map or something. But the main difficulty is showing that all these higher cohomologies are 0 for the de Rham cohomology. And so the way that we're going to prove this is we can do the quick calculation of the point manifold. So calculate de Rham cohomology point. Yeah, I'm going to call it star. That's our manifold, favor manifold. So what is this? This is going to be the set of closed P forms. Mod the exact P forms. So lucky for us, when P, in the whole construction of de Rham cohomology, the omega becomes 0 once you go past n anyways. So right here, since we're a point, we're a zero-dimensional manifold, is a zero-dimensional manifold. So our situation is only omega 0, which is C infinity, is non-zero. And this is just R, because the only functions from a point to real numbers is R. And then omega P for P greater than 0 is 0. So that makes our whole calculation business easier. We'll get that H0 dr of a point is R mod 0, which is 0, and HP of dr is going to be 0 mod 0, is going to be 0. So now that we figured out what it is for a point, we're going to have to figure out the de Rham cohomology. We're going to show that de Rham cohomology is a homotopy invariant. So our next task is show de Rham cohomology is homotopy invariant. Now the crux of the proof of homotopy invariance is this formula. It's Cartan's magic formula. So I'm going to write down the formula and I'm going to interpret it in a few ways. One of the ways which suggests how we'll use it, and one of the ways which suggests how we'll prove it. So let me first talk about how we want to use it. So Cartan's magic formula tells us that whenever we have, I guess, a manifold M, we have X, a vector field on M, then the lead derivative of X, with respect to X, is equal to the exterior derivative of the interior multiplication by X plus interior multiplication of the exterior derivative. So one of the things that we'll see, or one can prove, is that the lead derivative commutes with the exterior derivative. I guess the way that we should think about this is that the lead derivative is taking the time derivative of pullbacks by the flow, and the exterior derivative, importantly, commutes with pullbacks. So if we're doing this sort of situation, we should be able to pull the d out, take the derivative. At the end of the day, let me write this way. Interpretation 1. So this commutes with exterior derivatives because d commutes with pullbacks. So this means that Lx is a chain map from omega star of M to omega star. Maybe I should use a hash for my notation. Omega hash of M to omega hash of M, where I probably should have written this earlier. Omega hash denotes the whole chain complex, or cochain complex corresponding, the de Rham cochain complex. So Lx being a chain map, if we interpret it that way, this picture right here, this formula, maybe if I rewrite like this, it's a little bit more suggestive. I can write it as Lx minus 0 is equal to dix plus ixd. This expresses that Lx is chain homotopy equivalent to 0, where Ix is the homotopy operator. I guess the chain homotopy is the terminology here. The chain homotopy. Now, what does this say? This says that L sub x as a map on homology, so maybe I should write L sub x star from the de Rham cohomology HP dr of M to HP dr of M is the zero map. So it sends every differential form, every equivalence class, cohomology class, it sends it to 0. And the way that we should think about this is that L sub x is taking the derivative of a flow. Here. Eventually our goal is to show that when you have a homotopy, it does nothing to your cohomology class. And the Lie derivative is taken by taking the derivative of a homotopy, the homotopy that you get from a flow. So we could, in one sense, interpret Cartan's magic formula as an infinitesimal version of homotopy invariance. That when we have a homotopy that is the flow along some vector field, that let me draw some sort of picture. Let's say we have the manifold. This picture will come up later. We have a manifold, and then we have the interval I. And so we're crossing maybe the torus, for example. Here's our manifold, and then we can put the vector field x. Let's say it's the vector field which just assigns partial s, like the up arrow, to every single point. As soon as I've drawn enough up arrows to make me feel satisfied. So the flow corresponding to this vector field is just go up. It's going to be the assignment. You take a point, you take a time, and you map it to that point, and then, well, sorry, maybe let me call this S. And this will be your phi t, maps it to S plus t. So this vector field, X, gives us this flow, and what the Cartan's magic formula says is that if you are to take the derivative of this flow and see what happens to your cohomology class, it doesn't move. It stays the same. We're going to get that, if we believe that homotopy invariance is true, the thing that should happen is that as you pull back your omega along this flow, you try pulling it back using phi t over and over and over again, we should expect that we're going to get the same omega up to an exact form, that we get the same cohomology class, because these are just corresponding to like a homotopy. So if we, I don't know, are doing it and we keep getting the same, oops, this is the wrong. We keep getting the same omega no matter what time we plug in. If we take the derivative, we expect that to be 0. The derivative of the constant map is 0. And so that's the sort of thing that Cartan's magic formula is expressing, that the taking the derivative of homotopy invariance tells you that the flow, it tells you that the Lie derivative is the 0 map on cohomology. Just the same way that we expect, if we expect homotopy invariance, we should get Cartan's magic formula by taking the derivative. If we're starting with Cartan's magic formula, we're going to get homotopy invariance by integrating. But before we go into that proof, I want to talk about how do we prove Cartan's magic formula in the first place. Because even if we see that, okay, Cartan's magic formula leads to homotopy invariance or vice versa, we should also talk about how do we get to Cartan's magic formula in the first place. A lot of Stack Exchange posts like to prove Cartan's magic formula in slick ways using homotopy invariance, which is really taking the derivative. But we should have some sort of proof in order to not be circular. And the perspective that I really liked on this was through differential graded algebras. So we've been talking about the chain complex, the de Rham chain complex, omega hash. Maybe I'll use different notation or the same. I'll call this omega of m. I'm going to talk about the entire, instead of thinking of it just as a chain complex, thinking of it as an entire ring. So it's a graded ring with these graded components, omega 0, omega 1, dot dot dot, up to omega m, omega n of m. And this has a ring structure via the wedge product. The wedge product isn't commutative, but it is graded commutative. This whole thing turns into a differential graded commutative algebra, with the differential being d. But we should take an aside to talk about differentials or derivations. So I'm going to define for you a graded derivation. So let A be a graded algebra. Maybe a graded, we're doing the real numbers, a graded R algebra. A derivation, a graded derivation, sorry, is a R linear map. Sorry, I should say a graded derivation of degree k is an R linear map such that, let's give a name, R linear map, let's call it capital D, such that D of the P homogeneous elements gets sent to the P plus K homogeneous elements, and this is where the derivation comes into play. This is the going to denote the multiplication by wedge, since that's what we're going to use above. D alpha wedge beta is equal to, so this is where derivation comes into play. This is the graded form of Leibniz rule. Since we're kind of having to move the D all the way across A, we're going to get the whole degree of D over here and the degree of A. So I'm going to denote that using the absolute value bars around A of alpha wedge d beta. So why do I introduce this formalism? Well, every piece of Cartan's magic formula is a graded derivation. So the exterior derivative, d, is a degree +1 derivation. This rule right here, the second, the Leibniz rule, maybe I should put that in parentheses, looks familiar. It's just we replace this k with 1, and this is this negative sign that shows up in the exterior derivative, which also makes it into a differential, importantly. So then another term appearing is this Lie derivative. This Lie derivative is a degree 0 derivation. And this matches up with what we see when we're studying just vector fields instead of the whole de Rham algebra complex. When we're studying vector fields, we think of vector fields as derivations. And vector fields is really the same thing as taking the Lie derivative, just only for functions rather than for any tensors. You do the Lie derivative of a function is just apply x this function. We use the notation dot. So x dot f times g, we see this familiar rule of xf g plus f xg. And this being a plus rather than this minus sign business is because it's degree 0. So it's 0 times the degree of f, which is still 0. So that's great. Then the last sort of piece of the puzzle is the interior multiplication, ix. This is a degree -1 derivation. And then this formula that we see in Cartan's magic formula expresses this degree 0 in terms of these degree 1 and -1. Now, how do we interpret the right-hand side? So let me write down a little proposition for you. proposition slash definition, I guess. The graded commutator bracket so the way we define that is we're given two derivations. We do d1, d2 minus -1 to the degree of d1 times the degree of d2, and then we flip the order. So the graded commutator bracket of graded derivations is a derivation. Now, what we see on the right-hand side, so let me write this way. If we try taking the Lie bracket, or sorry, the commutator bracket of the derivation d and ix, what do we get? We do dix minus 1 to the degree of d. So d takes p forms and makes p plus 1. P plus 1 forms. So this is degree 1. And then interior multiplication, it's degree minus 1. And then this is ix d. And this whole thing is just minus 1. So minus 1 is plus. So dix plus ixd. So in this way, we can see that that right-hand side comes up in a very natural way. It's not just some sort of random commuting, and it's a commutator. It's just you have to interpret in the graded sense. So now, when it comes to a proof of Cartan's formula, Cartan's magic formula, what do? We see both sides are derivations, are degree 0 derivations. And then we prove both sides agree on generators of the Rham algebra. So globally, it's hard to say exactly what the generators of omega m are, but locally, the generators are going to be it's going to be zero forms, which are easy to understand. These are just functions. And then locally, we can write any one form as these a function multiplying well, we can write any p form as a wedge of exact forms. Locally, exact one forms df. So when we're proving Cartan's magic formula, what we need to do, we need to prove it for zero forms. So maybe let's see that real quick. So L sub x of f, for f a function, well, this is just x dot f. And on the other hand, if we do dix of f plus ix of d of f, well, this left-hand thing is 0 because, well, the interior multiplication takes in a p form and gives you p minus 1 form. This is already 0 form, there are no minus 1 forms. This is 0, so the differential is 0. So this is equal to 0 plus ix of, maybe I'll put parentheses this time, df. So this means to evaluate df at x, df at x, well, this is just x dot f. So these agree. Then let's talk about exact one forms. So the Lie derivative of df, well, the exterior derivative commutes with the Lie derivative, as we talked about before. So this is d of Lx of f. And on the other hand, we're going to have d of Ix of df plus Ix of d df. Well, df is exact, you take the differential. D squared is 0, is what I mean. So this right-hand term goes away, and we just get that d of ix of df. And what is this? This is d of df of x, which is d of the x dot f, which we can write as d of the lead derivative applied to f. So we also get the same thing. And so since these are at least local generators and derivations which agree on local generators, at least the ones we're studying, well, they only need to see a local part of the function, because the derivation of a bump function is 0, and so we can put in bump functions and use Leibniz rule in a clever way. So that proves Cartan's formula. And now let's use Cartan's formula using our sort of other interpretation as an expression that interior multiplication is a chain homotopy of the lead derivative to prove homotopy invariance. So let's put down our definition. Just as we saw that the interior multiplication was so sorry. Let me put it this way. When we're proving homotopy invariance, we're first going to start with our favorite homotopy, the straight line homotopy. So maybe I shouldn't have written this quite yet. Let me write down as a theorem. Theorem. Let's see. So manifold. Um, and then we're going to define this homotopy, IT, which is from M to M times I. So it's a homotopy into this product, which sends X to X comma T. Then we're going to define, I guess I won't write it yet. So then there exists homotopy operator, H, which takes in M cross I forms and gives you a lower dimensional E-1 form on M. And then for it to be a homotopy operator, what that means is that it expresses that I star at time 1 minus I star at time 0 is equal to HD plus DH. Right. So the thing that we have to do is write down what is our homotopy operator. And we're going to reference that picture that we drew earlier with the stacked tori, just as an example. Maybe I can copy it. I don't know if this will be fast. Let's see. And then I copy. Oops, it's refusing. Okay, let's try again. Oh, this is looking promising. Select only the right things and not the wrong things. Now we can copy it. Now let's go back down. Let me paste this down here. So here's our situation. We have M times I. In my notes, I've been using not the letters X, but I've been using the letters S for this vector field. So what do? We define this vector field S in X of M. And we define S in the following way. We say S at a point Q comma S is just equal to 0 So nothing in the manifold direction, and then there's going to be a partial s in the maybe a time s, let's say, in the vertical I direction. So now we define our homotopy operator. So given omega, I'll even write like this. This isn't how I wrote in my notes, but I can say we're going to define H. H is equal to, just as we saw that the interior multiplication was the ticket for the Lie derivative, we're going to find H to be instead the integral of pulling back interior multiplication by S of blank dt. So the idea is you plug in omega and you plug in omega here. And now what we need to show is that this is actually a homotopy operator. So I want to show, as I've written just a second ago, that I1 star minus I0 star is equal to, which order do I write it? It doesn't matter. HD plus DH. So let's see. Let's pick a omega, a P form, and let's evaluate. So evaluating the right-hand side, let's try a few terms. Let's see. So we can evaluate d of h omega. We can commute the exterior derivative with this integral. This is the same thing as differentiating the integral sign, at least in coordinates. This becomes an integral from 0 to 1 of it star of, I guess I'll use this notation for the interior multiplication to not confuse my i's with iotas. Omega dt. And then on the other hand, well, maybe I'll just write everything together. So the thing that we're trying to eventually compute is h of d omega plus d of h omega. We figured out what d of h omega is, and then h is just in this definition above. So this whole thing, if we combine the integrals, becomes this integral from 0 to 1 of it star of this interior multiplication d omega plus, plus d of it star, as we've written above, of s interior multiplication omega. This whole thing maybe in extra parentheses. I think I need dt. So to evaluate, we can commute using the naturality of the exterior derivative. It commutes with pullbacks to switch the order of the it. So this is the integral from 0 to 1 it star. So we're going to swap these, and then I'm going to pull the whole it out of everything. So this becomes s interior multiply d omega plus ds interior multiply omega. Now this, remember, was our infinitesimal homotopy invariance. This is our Cartan's magic formula. So this is the integral 0 to 1 of it star of the Lie derivative with respect to s of omega. It's Cartan's magic formula. Now, let's see. We can rewrite this interior part in order to integrate nicely. Let's say it star of the Lie derivative with respect to S of omega. By definition, more or less, we can translate. Let's call theta the flow associated to S. So rather than pulling back at time t, we translate the whole thing up by t or down in one of these directions using the flow associated to S. Then the Lie derivative is the derivative of a flow, right? So what does this become? This becomes, I guess I'm combining steps here, but this is d over dt of theta t star of omega. So this is taking the derivative at time t rather than at time 0, like you normally would with the Lie derivative. And then I can commute these two. So it's just d dt of I star 0 of theta t star omega. And what does that give you? That gives you that h of t omega plus d of h omega is equal to this integral from 0 to 1 of d dt I 0 star of theta t star omega. So this is equal to, by the fundamental theorem of calculus, we do this theta at time 1 and at time 2. There yeah. So this is I 0 star of theta at time 1 star of omega minus I 0 star theta times 0 star omega. And then this just becomes, doing this flow, this is I1 star of omega, and then theta 0, that's the identity. So this is just I0 star of theta, or of omega. And this proves that H is a homotopy operator. So the rest of the proof will continue by showing that, let me just sketch at least. We show that our homomorphism, this Rham homomorphism from Rham cohomology to singular cohomology, we show that I is a natural transformation, I suppose. We could view the situation as we have the category of smooth manifolds. I don't know how to denote this, smooth men. We have one functor, which is this HPdr, which goes to real vector spaces. And then we have this other functor, singular cohomology, HP. And we've so far constructed for each smooth manifold a map I going down, but we also want to show that they assemble together to be a natural transformation. And even more, we want this natural transformation to commute with the connecting map that you see in Merivia-Torres, and that'll let us do the induction. So now so there's this, and then show I commutes in Merivia-Torres. Now the Merivia-Torres induction goes as follows. You can start by showing the base case that I is an isomorphism for contractible manifolds. This isn't too hard to do. you just show that if you have a non-zero zero form on a contractible manifold, that's sent to a non-zero cochain, a non-zero cocycle, or I guess I should say, if you have a non-zero de Rham cohomology class that's sent to a non-zero singular cohomology class, and this isn't so bad. Part that's more interesting is the bigger structure of the argument, where once you have that base case that works for contractible manifolds, we start saying that it works for certain unions. So if, for sake of terminology, we'll say call M de Rham if I is an isomorphism, maybe I should say iso, for M. So the base case proves that all contractible manifolds are de Rham manifolds. And then we're going to do, I guess I'll call this finite induction, where we'll prove that whenever you have M covered by, let's say, U1 union dot 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 union, let's just do in the case of two. Whenever U is covered by two manifolds, or two open sets, U and V, U, V, and U intersect V, all de Rham, then M is de Rham. And the way that you prove that is using the 5 lemma and Mayer-Vietoris. So Mayer-Vietoris for de Rham cohomology gives you a sequence. Let's write it this way. Well, the middle term, the thing that we're interested in, is our manifold M, right? I should say de Rham cohomology. Then what does the Mayer-Vietoris sequence give you? You can, on one hand, restrict your differential form to the different components. So this is Pu, O plus, sorry, direct sum, P dr V. And then here's this connecting map. I'm going to denote it D from, and this goes to HP plus 1 dr of U intersect V. This is just expressing that when you have these two differential forms on these open sets, on their intersection, this comes from a right. I don't have this on the top of my head, but this is the Mayer-Vietoris sequence that you get, if I am not mistaken. Yeah. You should have over here. Oh, sorry. Yeah. I'm having my indices wrong. That's why I was confused. So this is not the connecting map. This is the difference. Difference. This is the restrictions. And then over here, there's this recognition. There's the higher map from HP minus 1 of U intersect V. And then you have HP minus 1 of U direct sum HP minus 1 of V. And then you'll similarly get the sequence. I guess I should put DRs over here. You'll get the same sequence, but getting rid of the DR and adding coefficients in R in singular cohomology. And then you'll get these maps downwards, which are the I maps. And because U, V, and U intersect V are all de Rham, that'll mean that this is an isomorphism, this is an isomorphism, this is an isomorphism, this is an isomorphism. So by the 5 lemma, that implies that this is an isomorphism. So that's kind of like our finite induction. And this will work whenever, not just with pairs of two, but when M is covered by U1 through UN, and all intersections of the UI are de Rham, then your manifold will be de Rham. So that helps you in a lot of cases. For example, if our manifold was compact, we could get a proof pretty quickly right now just by saying, okay, pick a metric on M, and then you can cover M with finitely many, I don't know exactly what you need, strictly geodesically convex neighborhoods. So these neighborhoods have the property that they're contractible, where the contraction is given by the exponential map, and the intersection is still like geodesically convex. So those are still contractible. So we've written M as this finite union of de Rham manifolds, which all have intersection, which are de Rham. And so already for compact manifolds, this finite induction is enough, plus some Riemannian geometry. If you want to go in general, there's some fiddling that you have to do using exhaustion functions, but I will stop for now. Thank you.